You step out of an 80-degree summer day, you walk through the terminal doors, and I mean, within 3 minutes, you are frantically digging through your carry-on for a heavy sweater.
Oh, yeah, looking for a jacket, a scarf, anything you can find.
Exactly. You're checking your phone to make sure you didn't, like, accidentally fly to Antarctica before you even passed security. It's just this universally baffling experience for you, for me, for anyone who travels.
Right. It really is.
So why is every major airport on Earth essentially a walk-in meat cooler?
Well, it's something you never really think about until you're the one shivering at gate B12. But for this deep dive, we're pulling from some incredibly detailed source material that looks at the hidden mechanical realities of airport HVAC systems.
And we've got some great sources today.
Yeah, we're going through insights from Ken Warren. He's a mechanical professional engineer and the Assistant Director of Aviation Facilities and Infrastructure at Seattle-Tacoma International Airport.
So he really knows the behind-the-scenes mechanics.
Absolutely. And we're also pulling practical terminal survival strategies from Clint Henderson, a travel expert from the Points Guy who, practically lives in these buildings.
Which is going to be so helpful for our listeners.
Right. And together, these sources show us that the thermostat isn't actually broken. The cold you feel is the result of this massive invisible engineering battle playing out right above your head.
Okay, let's unpack this because my mind immediately goes to the most basic operational question.
Yeah.
If the building is too cold, someone in management should theoretically be able to just turn a dial and set the entire terminal to, say, 72 degrees.
You would think so, yeah.
Right, because if I set my living room to 72, I'm perfectly comfortable. So there has to be a disconnect between the number on the thermostat and what is actually happening on the floor.
There is a massive disconnect. And interestingly, the engineering guidelines totally agree with your living room preferences.
Wait, really? They want it at 72?
Yeah. The professional organization, ASHRA, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, which is basically the absolute gold standard globally for how these massive systems are designed.
Right, the gold standard.
They actually recommend a very moderate temperature range for these public spaces. They suggest keeping things between 70 and 75 degrees.
Oh, wow.
Yeah. Year-round, facilities managers are usually targeting a sweet spot of 70 to 72 degrees.
Which means the ambient air in the terminal probably is hitting 72 degrees, but it just, it doesn't feel like it to the human body.
Exactly. What's fascinating here is that the raw temperature setting on the equipment is only one small piece of the puzzle.
Okay.
Human comfort, or what mechanical engineers specifically refer to as thermal comfort, is an incredibly delicate matrix.
Thermal comfort. Got it.
Right. It relies on ambient air temperature, sure, but it also relies on humidity, the velocity of the air moving past you, your individual metabolic rate, the clothing you have on, and something called radiant temperature.
Radiant temperature being the heat or lack thereof emitted from the physical surfaces around you, right?
Right. Think about modern airport architecture. Decades ago, terminals were more enclosed, heavy concrete structures.
Like bunkers almost.
Yeah, exactly. But today, the architectural trend is massive, towering walls of glass. So even if the ambient air pumped into the room is perfectly 72 degrees, if you are sitting near a 50-foot wall of glass on a cold, overcast day.
That glass is just radiating cold right onto your skin.
Precisely. It dramatically pulls your perceived thermal comfort down.
So setting the thermostat at home is basically like drawing a perfectly warm bath. You have a small enclosed container, you find the right mix of hot and cold, and the water just, sits there, mostly still.
That's a great way to put it.
But managing the thermal comfort in an international airport is, well, it's like trying to control the temperature of a rushing river while thousands of people are constantly opening and closing massive doors along the riverbanks all day long.
The rushing river is the perfect analogy to look at this, because the movement of the air is actually the biggest operational hurdle engineers face.
The movement, not the temperature itself.
Right. Ken Warren notes that what passengers are actually complaining about most of the time isn't a low ambient temperature setting at all. They are complaining about air currents.
Ah, so it's a breeze.
Yes. They are feeling the wind on their skin, and that wind strips away body heat.
Which brings up the obvious question. If the wind is what's making us cold, why does the air in an airport need to move so aggressively in the first place?
That is the million-dollar question.
Because, we aren't just feeling cold air, we're feeling a persistent draft.
To understand the draft, you really have to look at the entire building as a single pressurized vessel. Warren uses the metaphor of a big, blown-up balloon.
A balloon?
Yeah. To maintain indoor air quality in a massive facility with thousands of doors, the building requires what engineers call positive pressure.
Okay, positive pressure. What does that mean exactly?
It means the HVAC system has to continuously and actively push a high volume of air outside.
Yeah.
Imagine a balloon with a tiny hole in it. The air is constantly rushing out of that hole.
Right, which physically prevents anything from coming in.
Exactly. It's actively pushing back against the outside environment.
And considering where an airport is located, I'm guessing they're trying to keep out something specific.
You nailed it. You have hundreds of idling jet engines sitting just feet away from the terminal walls.
Oh, wow. Yeah.
You have ground support equipment, baggage tractors, and diesel trucks constantly circling the tarmac.
So it's an incredibly polluted, immediate environment.
Absolutely.
Yeah.
If the building didn't maintain that positive pressure pushing outward through every crack, door, and jet bridge, the exhaust and fumes from all those engines would be drawn right into the terminal.
Wait, really? So that freezing draft hitting the back of my neck when I'm like waiting in line for a coffee, that is actually the only thing keeping carbon monoxide out of the terminal.
Yes. It's essentially an invisible shield protecting the breathable air.
That is wild.
That's the reality of the engineering. Facilities managers are forced to prioritize safe indoor air quality over perfect thermal comfort.
Because if they lower the airflow to stop the draft and make you comfortable...
The terminal fills with jet exhaust.
Yeah.
Exactly. Maintaining that outward push across millions of square feet, from narrow corridors to giant open mall areas, requires moving an astronomical volume of air.
And when you move that much air, you inevitably create powerful currents and imbalances.
Precisely.
That completely reframes the experience. You are basically sitting inside a defensive breeze.
A defensive breeze. I like that.
But mechanically, delivering that much air into these specific types of buildings seems like a total nightmare. I mean, airports have these massive 50-foot vaulted ceilings.
They do, yeah.
So you have to push enough air in to create that positive pressure shield, but you also have to get the temperature right for the people walking around way down on the floor.
This is where we get into the really brutal physics of giant spaces. When airport HVAC systems are in cooling mode, they don't just gently pipe in 72-degree air.
What do they do?
The supply air comes out of the massive rooftop handlers at around 55 degrees.
55 degrees, that is a severe drop.
It really is.
You're dealing with a 17-degree delta just to condition the room.
And you have to remember the sheer scale of the room. Large spaces need extra mechanical force just to get the air to mix properly before it dissipates.
Right.
So that 55-degree air is pumped out at extremely high velocity. The engineering goal is for it to travel, mix with the warmer ambient air in that massive room, and eventually settle down to that comfortable 72 degrees by the time it physically reaches the passenger level.
Ah, okay. Which explains Warren's basketball arena analogy in the text.
Yes, exactly.
He mentions that phenomenon where you're walking through a stadium concourse or a giant airport terminal, and suddenly you are just hit by a freezing jet of air. But then you take 3 steps and it completely goes away.
Yeah, you've walked right through the supply stream.
That's crazy.
That was the 55-degree high-velocity air shot out of a vent 40 or 50 feet away. You just happened to cross its path before it had the chance to mix and reach the target temperature.
So you walked through the invisible crossfire of the HVAC system.
That's exactly what it is.
It's fascinating because that covers the cooling side of the equation. But what about heating? Like, if they can shoot cold air across a room, why does it always feel so chilly in the winter, too?
That's because of how differently hot and cold air behave in an open environment. Warren points out that cold air loves to travel.
Okay, loves to travel.
It shoots out of those vents and moves predictably. Warm air, on the other hand, is inherently lazy.
Lazy. You mean in the sense of thermal stratification?
Yes.
Because hot air naturally rises, so it has absolutely no desire to be pushed down 50 feet to the floor where we are.
Precisely. Warren jokes that warm air just wants to stop right out of the vent and sit there near the ceiling.
Just hanging out by the rafters.
Exactly. So if you are a mechanical engineer trying to force warm air all the way down to where the passengers actually are, in a terminal with vaulted ceilings, you are fighting a losing battle against thermodynamics.
So the heat basically pools at the ceiling, and the cold air just sinks right to the floor where we're all sitting.
Right. Trying to throw that lazy warm air down into the terminal requires specialized diffusers, massive fans, and incredible energy.
Wow.
So the chilliness you feel isn't just poor planning by the airport. It is an ongoing daily battle against gravity and the sheer scale of modern architecture.
Okay, so we've established that the physics of lazy heat and the necessity of the positive pressure shield are heavily stacked against us.
Very much so.
But looking at the sources, there is another layer driving these decisions. There is a very real financial incentive for airports to just let the building run cold.
Oh, the economics are staggering. If we connect this to the bigger picture, you have to look at the energy consumption of these facilities.
Right, the power bills must be insane.
SeaTac Airport operates the largest centralized heating and cooling plant in the entire Northwest. The source material notes that their electricity bills alone can hit $1 million a month.
$1 million a month.
A month. So energy efficiency isn't just some corporate talking point.
Yeah.
It is a critical operational priority.
And managing a $1 million monthly utility bill inherently affects how they view the people inside the building, doesn't it?
It absolutely dictates the philosophy of the space. In architectural and facility management terms, airports classify their terminals as transitory spaces.
Transitory space.
Right. You are not a resident. You are a temporary occupant meant to move through the space relatively quickly.
Okay, so they expect you to just be passing through.
Exactly. And because of this classification, managers observe passenger behavior and adjust accordingly.
How so?
Well, in the fall, winter, and spring, people travel with coats. Warren admits that if they look at the security cameras and observe that passengers are generally wearing layers, the airport will absolutely reduce the ambient temperature.
To save money on that massive energy bill.
Exactly.
See, here's where it gets really interesting, because I have to push back on that logic.
Oh, I don't blame you.
The airport is saving their $1 million by relying on the fact that I brought a sweater. But calling a terminal a transitory space feels entirely disconnected from the reality of modern travel.
It really does, especially lately.
If I am stuck in a winding security line for 2 hours, or a storm grounds my connecting flight and I'm sitting on the floor by the gate for 4 hours, I am not in transit. I am essentially a resident of that building.
There's an undeniable friction there. The engineering definition of a transitory space assumes a smooth, constant flow of people.
Which rarely happens.
Right. When that flow breaks down, when thousands of people are suddenly stationary for hours at a time, the thermal comfort model falls apart completely.
So they are actively choosing to let it be cold?
Yes. They assume you are moving, and they assume you have a coat. But understanding that dynamic actually empowers you to prepare for it.
So what does this all mean for us? We know the physics of lazy heat are against us. We know the building is constantly blowing a breeze to keep the jet exhaust out.
Right.
And we know management is actively lowering the temp to save on a $1 million energy bill. So how do we actually survive the terminal?
This is where the travel expert Clint Henderson comes in.
Oh, good. We need his tips.
He logs 150,000 miles a year, and he's turned navigating these microclimates into an absolute science.
Amazing. What's his first rule?
Based on the mechanical realities we've just discussed, his first rule is the most obvious one. Always wear layers.
Even in summer?
Even if you are flying from Miami to the Bahamas in July. You have to assume the airport is playing the transitory space game. You bring a sweater and a large scarf.
So you essentially have to pack for the microclimate of the building, not your actual destination.
Exactly. Second, you have to actively avoid the vents and the fans.
Right. Dodging that invisible crossfire.
Remember that 55-degree high-velocity air trying to beat the thermal mass of the room. You do not want to be sitting in its path before it has a chance to mix.
So you need to physically look up at the ceiling and the walls before you pick a seat at the gate.
Yes, scan for the vents. Third, stay as far away from doorways and jet bridges as possible.
Oh, because of the positive pressure.
Yes. If we go back to the balloon analogy, those entryways are the active battlegrounds. That is where the positive pressure is fighting the outside air to keep the exhaust fumes out.
So it's super drafty there.
Extremely drafty. The air currents there are going to be the strongest, and you will feel the wind on your skin constantly.
So if the doors are the coldest, draftiest spots, where should you actually go?
Henderson recommends looking for seats near restaurants, or, surprisingly, at incredibly crowded gates.
Crowded gates? Why?
Sitting near a restaurant allows you to benefit from the ambient heat spilling out of the commercial kitchens, and sitting at a crowded gate allows you to benefit from the collective body heat of the crowd.
That is brilliant.
You are essentially using human metabolism and kitchen exhaust to offset the lazy warm air from the HVAC system.
Wow. And he also had a very specific tip about where to put your feet, right? Pick a seat on the carpet whenever possible.
Yes, avoid the tile and the hard flooring. And this actually ties perfectly back to our earlier discussion about thermal comfort.
Specifically regarding thermal conductivity, right?
Yes.
Yeah.
While giant glass windows radiate cold onto you, the hard tile floor actively conducts heat away from your body.
Just sucking the heat right out.
Exactly. The tile draws the heat right out of your feet and legs, whereas the carpet acts as a mild insulator.
This entire deep dive completely changes how you look at the terminal. I mean, we started out wondering why the thermostat was broken, and we found out it's actually this highly engineered illusion.
It's all working exactly as designed.
Right. We explored the balloon effect, realizing that those freezing drafts are positive pressure shields keeping carbon monoxide out of our lungs.
A literal invisible shield.
We broke down the heavy physics of delivering 55-degree jets of air, the stubbornness of lazy heat pooling at vaulted ceilings, and the sheer economics of $1 million energy bill that incentivizes managers to treat us as transitory.
Which they will absolutely do if you let them.
Exactly. And we learned how to read the room dodging vents, avoiding the jet bridge battlegrounds, and finding a carpeted spot near a warm restaurant.
You really realize you aren't just in a waiting room.
Uh-huh.
You are inside a massive machine that is constantly fighting against the outside environment.
It's a machine. That's a great way to put it.
And synthesizing these engineering realities with the actual passenger experience, well, this raises an important question.
Go ahead.
If airports are currently justifying these freezing temperatures by classifying themselves strictly as transitory spaces, spaces where you are only meant to be passing through for a short time.
Right.
How will terminal design and HVAC philosophy have to fundamentally evolve in an era of increasingly frequent, massive climate-related flight delays?
Oh, that's a huge point.
As extreme weather events cause deeper cascading delays across the grid, passengers routinely find themselves stranded for days rather than hours. At what point does the transitory space excuse completely fail, forcing architects to finally figure out how to comfortably heat a 50-foot room?
That is something to think about the next time you step out of the sweltering 80-degree heat, walk through those sliding doors, and start frantically digging for your denim jacket.
You'll definitely look at the building differently.
You really will.
Yeah.
You aren't just putting on a sweater, you are putting on armor to survive $1 million battle against lazy heat and invisible wind. Stay warm out there.